Welcome to our Quantum Deep Dive. Today, we're exploring a 150-year-old idea that, believe it or not, has become this hidden engine behind modern quantum computing. It's called the Boltzmann equation, and this whole explainer is based on a fantastic essay by Jörg O. Snephead. So it all starts with this one huge question that basically obsessed the 19th century physicist Ludwig Boltzmann. He looked around at our world of predictable things, like pressure in a container or the temperature of a room, and he just couldn't shake this one thought. How on earth does all this order come from the frantic, completely random dance of countless invisible atoms? So his life's work, really, his grand ambition, was to build a mathematical bridge. A bridge that could finally connect the microscopic world of all those individual particles to the macroscopic world that we all live in and experience every day.
And this slide, it just perfectly captures that challenge, right? On one side, you've got the micro world. We're talking trillions of particles in what looks like pure, utter chaos. And on the other, the macro world, the world we can actually see and measure, governed by predictable physical laws. So, how do you get from one to the other? That was the puzzle.
Well, Boltzmann's solution was this absolutely brilliant equation. And it basically treated all of this chaos like a giant cosmic game of billiards. It was his way of tracking how the collective behavior of all these tiny colliding particles changes over time.
And, at its heart, the idea is surprisingly simple. The equation really has two main parts. The first bit describes the easy stuff, particles just moving freely in a straight line. But that second part, the collision term, that's where all the action is. That part accounts for what happens when they inevitably smash into each other.
That's exactly it. The free movement part, that's simple. But that collision term, that is the absolute heart of the equation. It's the mathematical engine that describes how these particles share energy and somehow forge predictability out of pure chaos. It's what pushes the whole system toward a stable, final state we call equilibrium.
And this thinking led him to his groundbreaking H theorem. So first, he defines this special value he just calls H. Then, and this is the key, he proves mathematically that the sum of all those particle collisions always causes H to decrease, no exceptions. And here is the genius leap. Since entropy, or what we think of as disorder, is the inverse of H, this was the first real proof of the second law of thermodynamics. He had actually found the microscopic recipe for the arrow of time. Incredible.
So for more than 100 years, this classical model was just brilliant. It worked. But as we started building technology on the scale of single atoms, a pretty big problem started to show up. Boltzmann's cosmic billiards model, well, it started to break down. And the problem was really fundamental. It was this. What if the particles we're tracking aren't tiny, solid little balls at all? What if, in the quantum world, they also behave like waves? Because that changes everything. You can't just model them as simple little collisions anymore.
The old classical equation just wasn't built for this new reality. For starters, it totally fails at the ultra-low temperatures where quantum tech has to operate. It completely ignores that particles can be in multiple states at once, that superposition. And it can't account for these deep quantum rules like the Pauli exclusion principle, which is kind of like a strict one particle per seat rule. So a new version was desperately needed.
And that is exactly what happened. Physicists didn't throw out the old idea. Instead, they took Boltzmann's 19th century masterpiece and gave it a 21st century quantum upgrade, sparking a total renaissance for this incredible equation. So what's the big upgrade? Well, the classical equation was all about figuring out the probability of finding a particle in one particular place. But the new quantized version is so much more ambitious. It uses this powerful tool called a density operator to track the entire quantum state of a system. Think of it like going from a flat 2D map to a full 3D hologram. It captures everything, including all that quantum weirdness.
And I want to be clear, this isn't just some abstract theoretical exercise. No, this revitalized equation has become an absolutely essential tool for the scientists and engineers who are out there building our future right now.
Just take quantum computing, for example. A quantum computer's biggest enemies are heat and information loss, a process we call decoherence. The quantized Boltzmann equation lets engineers precisely model this energy drain, making it absolutely crucial for designing more stable and more powerful qubits.
It's also a game changer for developing advanced materials. In a 2D material like graphene, electrons can move in some really strange and wonderful ways. The equation helps us understand and predict that movement, which is paving the way for revolutionary, ultra-fast electronics we can only dream of today.
And it even helps us build better sensors. The most precise instruments in the world, things like atomic clocks, are limited by tiny little thermal wiggles, or noise. This equation gives us a framework to analyze and minimize that noise, pushing the boundaries of measurement to a level of sensitivity that is just mind-blowing.
It's really such a powerful reminder, isn't it, that sometimes the key to unlocking the future is actually hidden in the brilliant ideas of the past. It really makes you stop and wonder, what other classic concepts are just sitting there, waiting for their own quantum renaissance to completely change our world?
Thanks so much for joining us on this deep dive. This explainer was based on the excellent work of Jörg Oa Schneppet. You can explore more of his analysis at schneppet.de. Thanks for listening.